first of all, if you look at this circuit, well, there's an internal battery. Maybe I should address that. Can I address that over here? Can I erase this? Can I erase this? If I tell you that a battery is represented by this, so this would be, this is called E, that's plus, that's minus, and then what you see in the book is that they'll draw like a rectangle like that, and that's the battery. Okay? So this is the internal resistance of the battery. If the current through the battery is this way, and that I is not me, that I is the current. Right. So I'm going to call this point A, because that's to the positive terminal, and I'm just going to call this point B. So the battery voltage is the potential at A minus the potential at B. Right? It's the higher potential minus the lower potential. So where do I start and where do I stop? I start at B and go towards A. Well, the rest of the circuit, I could take that path, but this is general, so I don't know what's over here yet. That'll depend on the problem. But I can go from B to A along this path. So if I go to the left, so I go this way. What should I write down when I go across this? Just the EMF, right? Just plus E. And what should I write down when I go across this resistor where the current is to the left in the same direction that I'm going? Minus IR. That's the battery voltage. And notice, in this case, the current is out a positive terminal, right? And that's what you see in this picture over here. This is like a car battery. This is the positive terminal of the battery. This is the negative terminal of the battery. And this battery is connected to, let's say, this headlight, something in the car, a headlight. But notice that in this picture, the current is this way, right? So the battery voltage will be the potential at A minus the potential at B. So it would be, well, E minus IR. Because this little R here is the internal resistance of the battery. So this that I wrote over here is this. On the other hand, if you have a battery where this is the internal resistance, that's the positive terminal, that's the negative terminal, this is E, this is R, right? And this is the battery now, right? And again, I'm going to call this point B, and I'm going to call this point A. So the battery voltage, again, is the potential at A minus the potential at B. And again, I start at B and I stop at A. So I start over here. So I'm going to go this way and I'm going to stop when I get there. But what if this is a battery that's getting charged so that the current is in the opposite direction? This I is the current, not me. And now I'm going to make the trip from B towards A through the battery, right? So I go like this to the left, and I go through the battery from minus to plus, so that's a plus E. But now, when I go through the resistor, I'm going in the opposite direction as the current through it, so it would be plus I times R. And that would be the battery voltage for this case, and this will be the battery voltage for this case. Two cases. So sometimes I'll ask you, what is the power output of the battery? Well, it's the voltage across it multiplied by the current. So if this is the voltage across it, just multiply this by the current. It'll be E times I minus I squared times R, only because you multiply that by the current, right? So that's this. But I don't like to memorize that formula. It's a battery, it's the current times the voltage. And how do I get the voltage across the battery? I just go from the lower terminal to the higher terminal using the same rules as Kirchhoff's laws. I don't want to memorize different formulas for different cases. I want to know the general method that would allow me to figure out, well, many problems, right? Without having to memorize, right? Now, in this case, that's, I think, in the next picture. So notice what happens over here in this picture. Okay, so let's make this a little bigger. So notice what happens over here. Now you have the battery in the car, but now we have an alternator here that's actually used to charge the battery, to keep the battery from draining. Right? And so notice that now the battery is getting charged by the alternator, and now notice the direction of the current into the battery. It's coming in at the positive terminal. This battery is getting charged. Right? And what is the power input into the battery? Well, it's the current multiplied by the voltage across the battery. But so it's I times the voltage across the battery. But in this case, the current is entering the battery at the positive terminal. So now the voltage across the battery is E plus IR. And if I multiply this by I, the current, I'm just going to get EI plus I squared R, which is this. But we're not really learning a new formula here, right? It's just the power is current times voltage. The voltage is the potential of the higher terminal minus the potential at the lower terminal. So I start at the lower terminal, go to the higher one, and I just use the rules in Kirchhoff's laws. And then I get this. So often you might see in the textbook, if you read the textbook, that the voltage across a battery is given by E plus or minus IR. So when do you use the minus? When do you use the plus? Well, given this discussion, you use the minus when the current is out of the battery, out the positive terminal. And you use the plus when the current through the battery is entering the battery at the positive terminal. Entering as opposed to leaving. And if you want a definition of the EMF of E, you could say that the EMF of a battery, right, is, well, it's the voltage across the battery when this term is zero. And there are two possibilities for that term to be zero. Either it's an ideal battery with no internal resistance, so the battery voltage is just the EMF, or there is an internal resistance, but then there's no current through the battery. So you can say the EMF is the voltage across the battery when there is no current through the battery. Or it's the voltage across the battery when, even if there's a current through the battery, but the battery has no internal resistance. Either way, the EMF will be the voltage across the battery when this term is zero, which will be when you have an ideal battery with no internal resistance, which is never really the case. I mean, 1 ohm is, but it's still there, right? And I is when there's no current through it. So this is from chapter 25, and I said, when I got to this point in chapter 25, I said, let me first discuss 26 and come back to this. Because now we can just see where this plus and this minus arrives now that I use what we learned from Kirchhoff's laws, going from one point to another point in this circuit. So now you're better prepared to learn. Okay. By the way, just so you know, so this is your car battery. Suppose you one day want to start your car, right? The engine, and it just goes click, 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 and it's just the battery's dead, right? And so you call AAA, then they come in, and then they want to sell you a battery. You tell them first, before you purchase that battery, check the alternator. Because it could be that the battery is not charging because the alternator is the one that's bad. So they sell you a battery, but if the alternator is bad, then it's gonna, the alternator is not going to charge the battery, and then the battery that you just bought, well, it's not gonna have any charge because it wasn't charged by the alternator because the alternator wasn't working. And now you gotta buy an alternator on top of the fact that you already bought a battery. So it may be that what's bad is the alternator. So you tell them, well, before I purchase the battery, let me make sure that the alternator is working. Right? So check it. That they have a way of checking it, and then no, the alternator is good. Okay, so then it's the battery. But it could be that the alternator is the one that's bad, and that your battery, well, it's dead because it wasn't charged by the alternator because the alternator wasn't working. Right? And then instead, what you need to do is buy the alternator and not a new battery. With the new alternator that works, then it will charge your battery that's still working, instead of having to buy both of them. Right? So, just so you know. Well, okay. So, I've touched with everything that I wanted to say about circuits. You know, I went from 25 to 26, back to 25, and I gotta talk about the RC circuit. I forgot to talk about the RC circuit.
Can I just ask for an example? Like, are you talking about the alternator earlier? When you jump a car, is that basically like you're charging it a little bit, so you would connect like positive to positive and negative?
So when you jump start the car, the idea is to use, well, your battery's dead, but your alternator is working, say. But the battery's dead, right? So what you want to do is you connect the battery in parallel, the one that you're going to use to start the car. So in that picture, it was 25. So what you do is so here's the battery. Let's say plus, minus, right? And this is your car battery, right? You got wires coming up, right? To the rest of the circuit, right? Rest of circuit, whatever that is. It includes the alternator and so on. But the battery is, there's no voltage across its terminals, or not enough to serve its function, right? So this is the bad battery. That's the rest of the circuit, you know, in the car. So what you want to do is you want to bring a good battery, right? And this is the plus, and this is the minus, and you want to connect the plus of this to the plus of that, essentially to replace that one, and the plus of this to the plus of that. So when this connection was not made, right? Usually the circuit is going to have current like this, right? Right? But because the battery is dead, then you don't get that current. So, because if the battery is dead, if the voltage over here is 0, right, then there's no electric field over here. There's no electric field this way, right? There's no electric field in this direction. So you don't have that, right? But if you connect the plus of the good battery to the plus of the bad battery and the negative to the negative, essentially this is the good battery. There is a voltage over here which is not equal to 0. This one generates this electric field which then continues over here. And then this one here, with this connection, just the electric field continues over there. And now this is your circuit. And as you get the alternator going, it'll charge your battery in the process. So you should jump start it and let it run, a few minutes, 5 minutes, 10 minutes. Once it's going, you can disconnect this one, and then you can charge this and charge it for like half an hour or something like that, right? The thing is that if the battery is bad, or if the battery is bad, then it's gonna
nothing will happen.
Yeah, you'll just use it for a while, and then once you drain it, then you'll have to do this again, or end up buying a new battery, so you don't have to do this each time.
Okay.
Yeah. but you connect the good battery in parallel with the battery that's,
I was thinking because of our earlier problem that it would just be your battery charging it enough to like start the car, but I see that it's like your battery's kind of becoming a part of the whole circuit.
yeah.
Thank you.
Another thing that you should do is, I don't know if I have good numbers. Consider this circuit. Suppose you have a battery, and let's say it's ideal. And the voltage over here, let's say is 20 volts. Let's see if the numbers come out so that we don't need a calculator. What if you connect a resistor like this? So I'll make it 1 ohm. And a resistor like this. And I make it 1 ohm. So they're in parallel, right? Question. What's the current through the battery? And what's the current through this resistor? And what's the current through that resistor? Let's call this I2, and let's call this I1. So, quick, how do you do this?
Would the voltage be equally distributed across each
They're in parallel, so if they're in parallel, they'll have the same
current? Or I mean, not current.
the same voltage. And it has to be because, see, the voltage across this battery is whatever the potential is here minus the potential there. But the potential here is the same as the potential there, right? Because you didn't go across anything. And the potential here is the same as the potential there. So this difference has to be the same as this difference because these two are equal. And it has to be the same as this difference. So the voltage across each of these resistors is therefore how much? 20 volts. And if you know too, if the voltage is 20 volts and the resistance is 1, then what's the current? So it would be, well, it's 20 volts divided by 1, so this would be 20 amps, and it's
also
20 volts divided by 1, it's 20 amps. Now, these 20 amps are going to come down here, right? And they're going to meet this 20 amps and give you what?
40 amps.
40 amps. So therefore this guy is going to be 40 amps. And then it's going to go this way. You got 40 amps. And then you got
20
amps going this way and 20 amps going this way. Yes? I actually didn't really use any equations, almost right. Now, consider this circuit. Now consider this other circuit. What if I have the same battery, plus minus 20 volts, and instead of just connecting one resistor, I'm using 1, 1, 1, so I don't need a calculator because I don't want decimal places and so on. And I have another one here which is also 1 ohm. So that circuit is the same as this. So what if I add another resistor in parallel? So now, what will be, so you're going to get current over here, right? And you're going to get current through this one, which is I1. You're going to get current through this one, which is I2. And you're going to get current through this one, which is I3. What will these currents be?
20.
Well, what's the voltage across this resistor?
20 volts.
20 volts. And the voltage of 20 divided by 1 ohm is?
20 amps.
20 amps. And what will be the current through this resistor?
20 amps.
20 amps. And what will be the current through this resistor?
20 amps.
20 amps. So now you have this. You got those 20 amps must have come this way, right? And you got the 20 amps coming this way, and that one is going to meet this one to give you what over here?
40 amps.
40 amps. And then that's going to meet this one going to the right to give you what over here?
60 amps.
Right? And then you get 60 amps over here. And then you got 60 amps. And it'll split. 20 are going to go this way, and then 40 are going to go this way. And then 20 are going to go to the right, and then the remaining 20 are going to go that way. So can you see that circuit now? So notice, if you have, bless you, if you, same source, 20 volts, right? But as you stack these resistors, right? Let's say just 2 versus 3, you're gonna get the same current through them. But what's different?
You're drawing on
The current through the battery is different. Here you only get 40 amps. Here you get 60 amps.